Hi Kiran, good evening. Can you hear me and see my screen? Am I audible and is my screen visible?
Yes, yes.
Okay.
I'm able to hear.
So I take this class every Monday 6 to 8, but I have some commitment next Monday, so I preponed this 12th session, which is also the last session here today. So this is going to be the last session of this course from my side, and we are going to solve questions on three-phase induction machine and DC machines in this course in today's class. Now I will start with questions on DC motors first. Then because they're a bit simpler. Now after that we will go for the problems of induction motor. Okay. No, this is not the first question. The first question. So Kiran, in every session, what I do is before I start solving questions, I ask for doubts to the students whether they have any doubt in the lectures of this week, the present week, and of any lecture of any other week. Or do you have any doubt in anything? If not, then we'll proceed with solving the problems. Okay, anyway, no response from your side. We'll start. Um, you can stop me and ask me questions if you have any in between. So this question says a DC series motor is drawing an armature current of certain value Ia and is operating under saturated magnetic circuit conditions. The torque developed in the motor is proportional to what? Now, in a DC series motor, what happens is the armature current and the field current, they are equal in magnitude because they're in series. That is why the name DC series motor. Now, the DC series motor, and it is drawing a current Ia. Now the question says that it's operating under saturated magnetic circuit conditions. So what do they want to convey by this statement? Now this is the BH curve. We mentioned, we discussed about this thing in last to last class when we were discussing magnetic circuits, that the BH curve of any magnetic material is practically a straight line or linear until certain value, beyond which it what we call is starts saturating, and it becomes like this. Now this is the saturation region, you can say, around this area after the knee, the saturation region, and before the knee is the linear region. Now the biggest difference between saturation and linear region is that in linear region the dBdh is quite large. The dBdh is quite large. dBdh is nothing but mu. It is mu is quite large, while here the dBdh or mu is quite small, which means that a certain change in h in the linear region would give rise to a large change in b. whereas the same amount of change in H in the saturation region would cause a very small change in B. In other words, in the operating condition of a motor, we can say if the motor has reached saturation, then the B, or the magnetic flux density in the magnetic circuit of the motor, it can be considered practically constant. Now, the torque is K phi Ia, K phi Ia for any DC motor. Right? Now, phi is some constant, say K primed, times field current IF, which is in this case equal to IA. Now, since flux is proportional to Ia, with increasing current, flux increases, but this happens in the linear zone only. The question is that this machine is operating in saturation, that is, flux also here practically become a constant. So in this equation, this part becomes a constant. So torque practically becomes proportional to the current. So this one is the answer. Any doubt, or we'll move ahead? Okay. Deepak, do you have any doubt in the week lectures of this week or previous weeks? Could you go through induction motor lectures?
Yes, sir.
Okay.
I attend three, 3 out of 4 induction motor lectures.
Okay. Okay. That's good. You have any doubt in those lectures or anywhere?
सर उसमें 1 minute sir.
Devak, since these lectures are recorded and uploaded to YouTube for everyone, it would be better if you can stick to English.
Okay, sir.
I also can't understand Hindi very well.
Okay, sir. In principle of induction motor, there is a ladder and ladder type concept which not understand properly.
Ladder type concept means
Means uh, consider so okay.
okay, we'll look into it. Let us complete the problems first. You have studied DC motor, Deepak?
Yes, sir.
Okay. So we'll now look into this question. A 4-pole DC generator runs at 1800 RPM. What is the frequency of the current in the armature winding? Now, a DC motor, say, say if I draw a DC motor like this, in general, DC motors, irrespective of number of poles or whatever, their circuit representation is this. Okay, the armature like this. Now, the current that it draws from the DC source is a DC current. That's it's a DC motor. But if you look into the armature of a DC motor, the current is AC. In fact, mm, except for reluctance machines, there is no machine, I believe, where the armature current is DC. At least I cannot think of any right now. Armature currents are AC. In a DC motor also, the armature currents are AC. Now, if the current that is entering the armature is DC, how does it become AC in the armature? Any idea?
Sir,
Hmm?
please once more tell what you said before I. listen not properly.
The current that the DC motor draws from the supply DC source is a DC current, whereas the current in the armature of a DC motor is AC current. Then who is doing the trick? Who is changing the DC current to AC current? It's a
Commutator.
generator. Yes, commutator. It's a generator. So the current is going out like this. If I call this plus and call this minus. The commutator, yes. Now, commutator and brush gear, basically. Commutator is on the armature, which rotates, and brush gear is on the commutator, and it collects the energy from the commutator. And the armature winding terminals are connected in the commutator. Now, if this is a 4-pole DC machine, then the poles look like this. Okay, and the armature is on the rotor here. And where are the brushes? The brushes are always put in the interpolar region. So one brush is here, one brush is here, one brush is here, other brush is here. Okay. Now this is a DC generator. Okay. So suppose let us take one coil side here and say it is rotating in this direction. Say in this clockwise direction it is rotating. Now when mm, just a second. When the when this one this coil side is crossing this pole here, it is having the maximum current through it, and at the brush it is having zero current, the zero crossing of the current. So basically what is happening is every time the conductor or the connection of the conductor crosses the brush, there is a zero current, because that is why the commutation is possible. If you see, this is one commutator segment, this is another commutator segment, and it is moving, and here is the brush, right? So the brush momentarily short circuits to commutator, and then moves to the, so this one is moving and then moves to the other commutator segment. So that is why it is necessary that when the coil is passing through this brush, the terminal, then the coil must have zero current. Okay. The coil must have zero current. Now, so if you look at this coil, in one rotation, it crosses through the brush 4 times. So we will call these positions as 1, 2, 3, 4. Okay. And now try to draw the current in the coil. If you to draw the current in the coil, say at position 1, it sees the first positive zero crossing like this. Then it remains constant on the next polar region under the pole. Again, it sees the next zero crossing at brush 2. Okay. Then it keeps going like this. Brush 3. Brush 4. Again, it returns to position 1. So this much current, anyway, the magnitude somehow they are not same, but you know that they will be same. So this is the whole picture of the current that is flowing through one coil, let us say, in one rotation. So how many cycles are here? Tell me quickly, how many cycles do you see? So how many cycles of current does the winding see in one complete rotation?
2 cycle.
2 cycle it sees. Now in one rotation it sees 2 cycles, and it rotates 1800 times in a minute. So in a minute it sees these many cycles. So in a second it sees these many cycles. So in a second how much it sees? That is the frequency. So what you get here is 60 hertz. So the armature current, armature winding of this DC machine or any 4-pole DC machine, when the machine rotates at 1800 rpm, sees a 60 hertz AC current. The armature current is 60 hertz AC current. Now there is a direct way of solving this using the synchronous speed formula for induction motor that we've used yesterday. Now this one is, do not think that this one is for for induction motor. This is a general equation for a synchronous magnetic field. Okay. Now for a synchronous magnetic field, so in this case, if you directly apply 1800 rpm times frequency, we have to find out by P is 4 equals, sorry, how did I do? 120 F by P equals 1800. If you do, you will get F equals 60 hertz. This is a direct way of doing, but I wanted to give you an idea of how the current flows inside. Okay, so although it is a DC motor, the armature current is AC, trapezoidal. Now there is something like, see, for an induction motor, you have squirrel cage on the rotor, you have armature on the stator. If you do reverse, if you put the armature on the rotor, squirrel cage on the stator, and you have to supply the armature through slip ring, that's a different thing. But that one also will work like a regular induction motor only. So for DC motor also, you can do the same thing. You can put the armature on the stator and put the field on the rotor. Then instead of having electromagnetic field, you replace them with permanent magnet. So it becomes a brushless DC motor because you do not need the brush anymore. The armature is on the stator and the field is replaced with permanent magnets, which do not require electrical supply. So in the brushless DC motor also, the current looks like this. Operating principle is exactly the same. Winding configurations are different, but the same thing, same motor. It's all about that if there are, it's all about Newton's third law. If one body is applying torque on another body, the another body is also having a reaction torque on the first body. Same thing. Anyway, so any doubt in this?
No.
Okay, we'll go to this question. This question is somehow, I do not feel technically correct, but anyway. The question says a DC series motor drives a load. The magnetic circuit of the motor is unsaturated, and the relation between the load torque and the speed is given by this, where K is a constant. For a speed of 300 rpm, motor line current is 10 ampere. For a speed of 600 rpm, the line current will be how much? Now, You see here the torque versus speed equation for the load is given. This is something you might not have yet encountered. So here it will be something like this. So there is it is dictated by the load. Okay, say for example, just it is not required for this problem, but just to give you an idea. Suppose there is a lift. Okay, so a lift is driven like this. So there is a pulley, uh, and it is being driven by a motor, and there is a string, and this is the lift. Now what happens is this lift has a total mass of mg, considering the passenger and the vehicle. So the tension on this string is mg. Sorry, tension on this string is mg. Now if the radius of this pulley is r, then the torque seen by the motor is rmg. Now you see this is a constant load, constant torque load. So an elevator is a constant torque load. On the other hand, if you look at the fan, for a fan the torque is proportional to omega squared. Okay, so the relation between torque and the speed, that would depend on the load, how the load is. If it is a viscous kind of load, you understand, no, the fan is a viscous type load. Same thing, say if you have a turbine of a ship, that is also a fan basically. The medium is different, but that is nothing but a fan. For that case also, it is torque proportional to omega squared. Okay, so that relation is given here. So the mechanical engineers or whoever have done experiments and have found out that the torque and the speed are related by this equation. Now a DC series motor is used to run this load. Now at a speed of 300 rpm, the motor line current was 10 ampere. We'll quickly write the equations for DC series motor. So torque is, I'm just writing K1 phi Ia. Okay, and so what we have to find out is the relation between speed and current. That's what we have been asked to find out. Okay, now phi flux, since this is unsaturated, is again linearly related to current, some constant K2 into Ia. So we can say from here the torque is K1 K2 Ia squared. Okay, again torque is given by, now see, this is the motor developed torque at steady state. Steady state means when the machine is rotating at constant speed. The machine is rotating at constant speed means the net torque on the system is zero. So the motor torque must be equal to the load torque at steady state, right? So at steady state, motor torque must be equal to the load torque. And mechanical loss also, but that is not mentioned here. We'll not look into it. So we can write TL equals to K1 K2 I squared. Now we will substitute TL with K omega to the power 1.4 equals K1 K2 I squared. So from here we can write that omega to the power 1.4 equals some other constant K3 I squared. So this is the relation between the speed and the current of the system. Now you have to simply put it like this. So for a 300 rpm, the current is sorry, for a 300 rpm the current is 10 ampere. So how much it is for 600 rpm? To the power 1.4. So basically you have to solve this, and what you will get is ia equals 16.24 ampere. Nothing much. Is it clear? Okay, we'll go to the next question then. This question is about a DC shunt generator. Shunt means parallel, okay? So DC shunt generator means the armature circuit and the field circuit, they're parallel to each other, okay? Now the DC shunt generator delivers 50 kilowatt power at 220 volt with prime mover rotating at a speed of 1000 rpm. The armature and field resistances are given. Calculate the speed of the machine when it is running as a DC shunt motor and taking 50 kilowatt at 220 volt. Okay. So do you know what is a prime mover? See, it's a generator, right? Generator means it converts mechanical power to electrical power. So mechanical power is coming and the generator is converting it to electrical power. So the mechanical power is delivered by this prime mover. So it may be a turbine, maybe it's a turbine which is connected to a generator. The turbine is being rotated by steam or water, whatever. So that delivers the mechanical power, and the generator develops converts it to electrical power. That's a prime mover. The prime mover is rotating at a speed of 1000 rpm, so the machine is also rotating at 1000 rpm. No gear is involved. The armature and field resistance are given. Okay, so now what we have to do is in order to relate the motoring and generating action, we have to find out the motor constant. Okay, that will allow us to relate. So we'll first draw the circuit, shunt generator. So this is the armature resistance, field field resistance, like this. Okay, now it is supplying a 220 volt line, and it is supplying a 50 kilowatt of power to this 220 volt line. So the total current that it is supplying, ia, so we are talking about generating mode now. The current, line current, that it is called line current, that it is supplying is 50 kilowatt by 220 volt. That will be something. Let me just open my solutions. Mm, yeah, it will be 227.3 ampere. 227.3 ampere. So this much current. Now we see the whole generator as a block. So it is delivering 50 kilowatt to a 220 volt supply. Means this current is definitely 227.3 ampere. Okay. Now this is a field winding. We are talking uh, about the steady state. Now steady state, at steady state, the inductor causes no average voltage drop across it. The average voltage across an inductor at steady state is zero. Okay. So the voltage across the field winding resistance is 220 volt. If this is 220 volt, the field winding resistance is 100 ohm. So the field current is 2.2 ampere. Okay, 220 volt by, okay, I'll write volt by 100 ampere, that is 2.2 ampere. 227 I wrote, I gave it 222. Okay, now if you apply KCL at this node, what you get is the armature is delivering a current of 229.5 ampere. Now this is causing a drop in the armature circuit resistance. So that is how much? 229.5 ampere current is flowing in 0.01 ohm resistance. So 2.295 volt is dropping. So let us say 2.3 volt is dropping across the armature circuit. From here, we can find out the back EMF, not the back EMF, it's a generator, so it's a developed EMF. So the EMF E will be 220 volt plus 2.3 volt plus 2.3 volt, which is 222.3 volt. So this generator is developing a 222.3 volt, of which 2.3 volts drops across the armature circuit, and that is why it is delivering to 220 volt DC source or DC load in this case, maybe a grid. So this, and it is also supplying the field circuit, Okay. So what we can say from here, what we can find out from here is the motor constant K phi. We know that E is equal to K phi N. We can find out the value in SI unit also, but we need not for this case. We will see why. So if E is K phi N, what we have is, okay, let me write it somewhere else. If E is K phi N, then 222.3 is K phi. This K phi is the motor constant, because you see it's a shunt motor and we are not having any control on the field current. So the field current remains constant, so the flux remains constant. So K phi is a constant times N. It is how much? 1000 RPM. 1000 RPM. So K phi becomes 0.2223. We will write the unit, it becomes volt per RPM. Right. Now this is the K phi of the motor. Now, if you keep the field constant in the motoring mode also, this K phi is not going to change. That will remain the same. Now the next part is calculate the speed of the machine when it is running as a DC shunt motor and taking 50 kilowatt to 20 volt. Am I going too slow? I'll copy this and this I will remove. It is now working as a motor. Okay. So it is now taking power from the grid. But you see here one thing, the field circuit current and voltage does not change because it doesn't understand whether it's a motor or a generator. What it sees is it is connected to 220-volt grid. Right? Now it is now taking a current, taking 50 watt. So the current will be the same. Line current will remain the same as before. It will be 50 kilowatt. So 227.3 3 ampere current it is drawing, of which 2.2 ampere goes away here. So the armature current becomes IA equals 225.1, 225.1. So this is the armature current. Now this causes a drop here. This causes a drop here. So 225.1. So what is 225.1 times 0.01 is the armature resistance. So this gives you 2.25 volt. So this causes a drop of 2.25 volt here. So from now, from this diagram, if you find out, if you apply KVL, what you get is 220 volt is E plus 2.25. So which gives you back EMF of around, it's 218,217.75 volt. This is a back EMF. This motor is developing. Okay. So basically you can understand that this is a back EMF like this. So if I draw it here once again for you, just take this idea. This is important. This is a back EMF, okay, armature, and the back EMF has a polarity like this, and a DC current is flowing in this direction. So basically you can call this as a DC source which is absorbing energy, So the motor is absorbing electrical energy, and where is this energy going? This is being converted to mechanical energy. So it is absorbing electrical energy, which is being converted to mechanical energy. So basically, if you multiply back EMF with armature current, from there, if you subtract the mechanical losses, what you get, is the power available at the shaft of the machine, the actual mechanical power available at the shaft of the machine. Anyway, so the question asks when the same machine is delivering 50 no drawing 50 kilowatt of power from the source as a motor, how much, what is the speed of the motor? So we know the back EMF, we have found out the DC motor constant. From here you can find out the speed. Since we have to find out the speed in RPM, and this K5 we found out in volt by RPM unit, we need not do any trickery or any change in unit. All we have to do is simply divide E by K5, which is 217.75 by 0.2223, which will give you around 979 RPM. This is the answer. So the same machine when run as a motor, and if it is drawing 50 kilowatt from the source, it will rotate at 979 RPM. Any question? It's simply application of KVL and KCL, nothing else. DC motor problems are all about these three equations. One is torque is K5 IA, and back EMF is K5 omega. This K5 are same if you calculate in SI unit. and KCL, KVL, and other basic things like power is torque times omega and all. Okay, any doubt? Can you prove that this k phi in torque equation and the k phi in back EMF equation, they are the same? See what I told you, the power absorbed by the armature is back EMF times armature current. So is E is k phi omega, then k phi omega times Ia, this much power is absorbed. Now this power is converted to mechanical power. So this is equal to omega times T. T developed, torque developed, or let's simply T. Now if you cancel omega from both sides, what you will get is T is k phi Ia. So why I'm saying torque developed is that the torque is developed by the motor, and there is some loss, mechanical loss, and core loss is considered here. Core loss is also reflected as a mechanical loss because it's nothing but eddy current breaking and all. Now, from the developed torque has to supply those two losses, and what is left goes to the shaft. This is also called sometimes shaft torque, shaft power, or sometime somewhere you will get to see this term called BHP. BHP full form is brake horsepower, which also means the shaft power. Okay, any doubt? All right. If not, then we'll go to the next question. A 1 kilowatt 220 volt DC shunt motor has armature circuit resistance of this much, field circuit resistance this much at no load and rated voltage. The motor runs at 1000 rpm and the line current drawn by the motor is 10 ampere. At full load, the motor draws a line current of 50 ampere. Neglect armature reaction, find the full load speed of the motor. So basically, the motor is there, single phase, not single phase, a DC shunt motor. And when there is no load, it runs at 1000 rpm. When there is load, the speed drops. No, is the speed drops definitely, and the armature current increases to 50 ampere. No load current was 10 ampere. The question is, what is the full load speed? Now, the motor is not delivering any torque to any load. It is no load, running at no load. Still, it is drawing current. That means it is drawing power. Where is this power going, Deepak? It is at no load. Why does it need to draw power? This is required to supply the losses of the motor. So if it is 220 volt DC and drawing 10 ampere current means it is drawing 2.2 kilowatt at no load. So the machine losses are 2.2 kilowatt at no load. Okay, at full load what happens? Like transformer only. So in this case also the core loss changes because the speed changes, and definitely the copper loss increases. Anyway, we will not go into that details in this problem. It's simply KVL again. So we'll solve two circuits, and again the approach will be same. No load data is given from which we will find out the motor constants. Then we'll find out the full load uh, speed. So let us draw the circuit. Again, DC shunt motor. I'll draw it here. Do I still have it in the clipboard? Yes. I will quickly erase this. Oh, it's a motor. Sorry. Elements. Why is it not going? Anyway, so this is the DC shunt motor. Now at full load, sorry, at no load, 220 volt, it is drawing 10 ampere of current. So we're not talking about no load. 10 ampere current, and the field circuit is 100 ohms. So 2.2 ampere will go, and the rest 7.8 ampere is going to the armature. Now you see there is a drop here once again, which is 7.8 times 0.1 ohm. So 0.78 volt drop in the armature circuit resistance. So 220 volt, of which this much drops, so this becomes 219.22 volt. So this much is the back EMF of the motor at no load when it is running at 1000 rpm. The same approach, E equals k phi n. If you do not convert the k phi value to SI, you make sure that you are not messing up with the units. That is why I am writing the units. Or if you want to be on the safe side, always convert it to SI. Anyway, so k phi is E by N, which is 219 by 1000, 0.22, 0.21922 volt per RPM. Okay. Now, now this is done. Now we have to look into the full load condition. The motor is drawing a line current of 50 ampere. Once again, I will copy this from my clipboard, paste this from my clipboard. Armature current, field current I am not changing. It's the same, remains the same, 2.2 ampere, right? But now the current it is drawing, because it has been loaded. So what happens if it is loaded? If it is loaded, the speed drops. If the speed drops, the back EMF drops, because E is k phi n. Since the back EMF drops, the supply voltage is same, back EMF drops, so the current, which is given by V minus E by R A, since E drops, the current increases. So that is why on loading the current increases. Now the current has now become 50 ampere, of which 2.2 ampere goes away, and we are left with 47.8 ampere here, of which and this causes a drop here. It's 0.1 ohm, so 4.78 volt. Now 220 minus 4.7 is 216, 215.22 volt. So when the machine is rotating, is delivering full load, the back EMF becomes this. Now, if you simply compare this value, the back EMF of the previous case and back EMF of this case, you see the back EMF has dropped. Why? Because the speed has dropped. And since the back EMF has dropped, it is now drawing more current. The armature was drawing, say, 7.8 ampere current before, it is drawing 47.8 ampere current now. Now we can find out E is k phi n, so n is E by k phi. Our k phi is volt per rpm, so what we will get is directly in rpm, 215.22 by 0.21922, which will give you a speed of 981.7, say 982 rpm or whatever. Okay, any doubt? Simple questions, just applying kvl, nothing else, and using the equation c equals k phi n, t equals k phi I. Okay. Look into this question. A 220-volt DC series motor takes 10 ampere when giving its rated output at 1200 rpm. Okay. Now, its armature resistance is given, field resistance is given. It is found that to obtain rated torque, so when this, okay, obtain rated torque at starting, resistance R1 has to be added. To obtain rated torque at 1000 rpm, resistance R2 has to be added. Find the value of R1 plus R2. Now try to understand the scenario first. Then we will solve the problem. Read the question once more. So DC series machine takes 10 ampere when given its rated output at 1200 rpm. Since they are saying rated output at 1200 rpm, that means they're talking about the mechanical side. So it's the rated torque at 1200 rpm. Now its armature is given, found that to obtain rated torque at starting, some resistance has to be added. Okay. Now what happens at starting? N is 0 at starting, right? In any, now since n is 0, back EMF becomes 0, and the current, say, is V minus E by R. Now since this E becomes 0, if you simply connect a standstill DC motor to a DC voltage supply, the current that it draws is V by R. Now just to give you an idea, see for example both the cases. At no load, see, it's this machine is rated for 220 volt. At no load, the back EMF was 219.22. At full load, it reduced only to 215.22 volt. Try to get an idea here. Okay, that if it is a 220 volt DC motor, the back EMF is somewhere here at full load also. It can never happen that a DC motor rated for 220 volt has a full load back EMF of 10 volt. Okay, it can never happen. Why not? Because the armature circuit resistance is very small, very small. Since the armature circuit resistance is very small, even a very small difference between V and E can cause sufficient amount of current to flow through the armature. Now if you say that there is a motor which is rated for 220 volt and the back EMF drops to 10 volt at full load, that means the 200 and there is 210 volt drop in the armature circuit resistance for a 220 volt machine. So that machine is definitely having a lot of armature, lot of copper loss in the armature. So this is why I am telling all this, is to give you an idea of the relative magnitudes of the supply voltage or the rated voltage and the rated back EMF of DC machines. They are like this. Okay. So starting now, if that back EMF becomes 0, so definitely the machine is going to draw a very large current. Why I said this is, sometime you might have a confusion in your mind like I had in my first year. So the resistance must be stopping that current, but the resistance is not large enough to stop that current. So to protect the machine, you have to connect another resistance in series. Say you call this starting resistance, which you gradually drop, which you gradually reduce when the speed increases. Speed increases means back EMF starts coming, and you keep reducing, and sometime you cut off the resistance, short circuit the resistance. That is how a DC motor is started. Now, this question says, mhm, armature resistance is 0.01 ohm, and this found that to obtain rated torque at starting, a resistance R1 has to be added. I solved this question in some fashion, but now I am thinking it can be done in a easier way. No, anyway. So we'll start writing the equations for a DC series machine, unsaturated DC series machine. So for any machine, any DC machine, not any machine, any DC machine, torque is K phi Ia and back EMF E is K phi omega. Okay. Now phi is some other constant, say I call this K1. K1 times field current. Now for DC series machine, this field current is equal to the armature current, right? This DC series machine, armature circuit resistance, field circuit resistance, this. So this is armature resistance RA, this is field resistance RF, this is CMFE. It is working at a motor, so current goes in, and this is the supply. Okay. So from here you can see that the same current flows through the armature and the field. You may or may not draw the field while solving the field inductance, because we are not talking about transient here. We are talking about steady state. Steady state, the average voltage in the inductor is 0, right? And in this case, it is anyway DC steady state. So V is L di dt. Current is constant at steady state, so V is 0. In AC circuit also, instantaneously it is not 0, but on an average, if you find out, the average voltage across an inductor is 0. Similarly, you will find out the average current through through a capacitor at steady state is 0. When I'm saying average, I mean average over a complete cycle, one time period. Anyway, so yeah, some data is given. The 220 volt DC series motor takes 10 ampere when giving rated output. Let us see what all we can find out from the given data. So from here, these two, what we can write is torque. Say if I call this 1, if I call this 2, so 1 now becomes torque equals K1 Is squared, and back EMF E becomes K1 Ia omega. This K1 we will call K prime. It's a constant. See, all this I am equating these constants. I can do them only when I am writing all of them in SI units. Okay, then only they will be magnitudinally equal. All right, so these two equations we have. Now, DC series motor takes 10 ampere when giving rated output torque as 1200 RPM. So let us use this equation, equation 3. Mm, yeah. So now it is drawing 10 ampere of current, right? And this is back EMF E. Now I will apply KVL here. What I will get is 220 is back EMF plus the ohmic drop, which is 10 ampere times the two resistances which are in series, armature and field resistance, which are zero point 0.1 and 0.5 ohm, so 0.6 in total, which gives me back EMF of this becomes 6, so 214 volt. Here also you see the machine is rated for 220 volt. At full load, the back EMF to 214 volt only. Okay. All right. Now, if it is 214 volt, from equation 3, we can write 214 equals K prime times IA times omega. So IA is 10 and omega we will write in SI because we have mixed up many things here. Let us not take any risk. So 10 times 1200 RPM. Hey, what is happening? Yeah. 10 times 1200 RPM. RPM converted to this will be 2 pi by 60. So pi by 30. This becomes radian per second. So K prime becomes, if you calculate, what you will get is 0.17 volt per radian per second, or you can say volt second per radian. Volt second per radian. So this is the motor constant that remains constant throughout. And we are trying to get rated torque at starting, so we will find out the rated torque also. How much is the rated torque? We now have enough data to find the rated torque. If I call this equation 4, just remove them. Then point 4, what we get from 4, what we get is rated torque. This is the rated torque definitely, because the calculations are all for rated conditions they have mentioned. It is K prime times IA squared. So K primed times IA squared, which will give you 17 Newton meter. From here I did from, if you take the decimals you will get something 17.8 Newton meter. Okay, now we have got as much data as we could. Another question says it is found that to obtain rated torque at starting, resistance R1 has to be added. So let us see what is the condition at starting. So I have already explained why we need to add resistance in series at starting. Now the resistance has to be calculated such that we get rated torque at starting itself. So at starting, what happens? Speed is 0. That means back EMF is 0. So the equivalent circuit becomes like this. Back EMF is short circuited now. Back EMF is short circuit. This is the equivalent circuit. And there is one more added resistance now. So this is the motor, one more added resistance. This is 220 volt. This is R1 and this total is 0.6 ohm. Now you see torque is K prime times Is squared. Okay, K prime is given, torque is something we know. Now we want rated current at rated torque at starting. That means we want rated current at starting. So the question boils down to what should be the value of R1 so that we get rated current at starting. So since there is no back EMF, what happens is the rated current is how much we found out? Oh, it was given 10 ampere. So 10 ampere current must flow when just a second here, 220 by R1 plus 0.6. Or you can find out the torque also from where you need not, because this equation tells us that k prime is a constant. So even at starting also, if we need rated torque, we will have to let the rated current flow. Now, if you solve this, you should get R1 as 22 minus 0.6, right? Which is 21.4. 21.4 ohm. Looks like we need not had to calculate this one, but anyway, this is one. And again, to obtain rated torque at 1000 rpm, a resistance R2 has to be added. So what happens at 1000 rpm? Now there is back EMF, right? Now there is back EMF. Now what to say? Can you realize why we have to connect a resistance in order to get the rated torque at 1000 rpm? You see, we were getting a rated torque at 1200 rpm. Now we want it at 1000 rpm. So 1000 rpm means the machine back EMF has now reduced from the rated value. But we want the same current. So V minus E has reduced. Sorry, E has reduced. So V minus E has increased. But we want the same value of current. So this R must be increased. That is why we have to connect another resistance R2 in order to get the rated torque at 1000 rpm. Without this R2, we get it at 1200 rpm. Now at 1000 rpm, the back EMF we can find out, it was here, K primed IA omega. K primed IA omega. Since we are trying to get the rated current, the rated torque, so the current must be rated, dictated by this equation. So K primed is 0.17, IA is 10, omega, we are doing everything in SI. So omega is 1000 times pi by 30, which gives you a voltage value of 178 volts. So you see, at 1200 rpm, the back EMF was 214 volt. Now, in order to get the rated torque at 1000 rpm, the back EMF must be 178 volt. Back EMF has dropped, so the current will tend to increase. In order to get the 10 ampere current, rated current, we have to increase the resistance. That is where this R2 comes. Okay, these realizations are important. That's why I'm saying without all this realization also you can solve these problems, but somehow these are important for you to, what to say, foresee situations. Anyway, so this is 220 volt, 220 volt by R2 plus 0.6 will give you again the rated current. Since we are trying to get rated torque, the current is rated current here also. So this is 10. No, this is 220 minus E, right? 220 minus 178. So it becomes here 22 by 10, 2.2. I'm making a mistake here. 22, 2.2. How much are you getting? I think I made a mistake. 2.2 minus 0.6, 1.6 are you getting? Where is my calculator? No, 3.6. Oh, this is 220. So it is at 42. 42, 4.2 minus 0.6. 3.6. Oh. So the question, so the problem is done. The question has asked you to find out, because it is an MCQ maybe, I think, what is the value of R1 plus R2. This carries no significance though, this value of R1 plus R2. This is 24, 25. Oh. Okay, any doubt in this question? I did this question very slowly to give you, so that you do not miss these ideas. But what happens when the loading condition changes? What happens if you try to get rated torque at different speeds? Kind of a good question this is. Is it clear? If so, then we'll go to the next question, which happens to be the last question on DC motor. The no load speed of a 220 volt separately excited DC motor. Separately excited DC motors are the easiest possible DC motors, because field and armature you can control separately. It is a field winding, which is most of the cases supplied from the same supply from where the DC motor is deriving power. And this is the DC wind motor like this. Now for this, they are saying the armature resistance drop and the brush drop are neglected. Okay, field current is kept constant, so phi is constant. Torque of the motor for an armature current of 10 ampere, we have to find out. Okay, how do I find out? Ah, they're saying no load speed is 220, is 1500 rpm. No load speed is 1500 rpm at 220 volt. So E is K phi n. Okay, so they are saying armature resistance drop and brush drop are neglected. So if armature resistance drop is neglected, then V becomes E. Not a very practical assumption though, but anyway. So from here we can find out K phi as V by N is 220 by 1500 volt per RPM. The torque of the motor for an armature current of 10 amperes. So torque is K phi I. Okay. So you see, we have to convert this to SI. 220 by 1500 into pi by 30 into current is 10 ampere. So what you get is 22 by 15 times pi by 30, 14 Newton meter. Okay. Now we'll solve the three induction motor problems at the beginning. Three-phase 50 hertz 10 pole induction motor. So runs at no load, sleep of 5%. With full load, sleep becomes 10%. Find the percentage speed regulation of the motor. Yesterday we saw what is voltage regulation. Speed regulation is the same. How much speed changes from no load to full load. Now we have to find out the no load speed. The no load sleep is given. Thus from here we can find out the no load speed. So what is the synchronous speed? (600 rpm), and they have given the sleep. Sleep is ns minus nr by ns. So 600 minus nr by 600 is 0.05, which gives you an nr of 600 minus 600 times 0.05, 570. 570 rpm. This is the no load speed. Now full load sleep is 10%. So synchronous speed remains the same because frequency is same. This is now 0.1. So 600 minus 60, 540 rpm. The percentage speed regulation of the motor. So the drop is 30 by 570 into 100%. So it is 300 by 57, 5.26%. One doubt I have, find the percentage speed regulation. See, in transformer, the voltage regulation is done with respect to the no load voltage, which is the rated voltage. But for induction motor, the rated speed is the full load speed. Okay, so it should be the full load speed 540. So you go 5.55%. Okay. We'll go to this question. If there is no doubt, if there is a doubt, you tell me. This is a formula based question. There is an induction motor. Shaft power and mechanical losses are given. It is known that stator losses are 0.3 times rotor losses. At rated load, find the percentage efficiency. Okay. Now we'll quickly look into the power flow diagram of an induction motor. So this is the stator, and it supplies power, it receives power from the grid. So this is the input power. Now the stator has some loss. The loss is the stator copper loss. So copper loss of the stator side. Now the rest of the energy flows to the rotor through air gap. The energy or the power that flows from the stator to the rotor is called PG, or back or gap power, PG. Now the rotor experiences again rotor copper loss, and rest is then developed as a mechanical torque, so mechanical power. Now this is a developed mechanical power from which the iron loss and the mechanical loss means due to friction and windage goes away, and what we get is what remains is the shaft power. This is what we get at the shaft of the induction motor. Okay. Now the efficiency is then definitely the output, which is the shaft power, by the input power. Okay. So we'll do this. The mechanical loss at rated conditions are given. Sorry, shaft power and mechanical loss. So mechanical loss is more than shaft power. We'll keep listing them. So shaft power is 90. Mechanical loss is 500. Okay. So here the core loss is not considered. They have not talked about core loss, so we need not talk about it. So from here the mechanical torque that we get, so from the figure you can find out that Pmech, the developed mechanical power or the power output from the rotor, is basically addition of these two powers, which is 590 watt. Right now the rotor ohmic law, the total power that comes to the rotor is Pg, and that is divided into two parts. One is SPG, another one is 1 minus S PG, of which this one is the rotor copper loss and this one is Pmech. This one is Pmech, mechanical power. Right. So they have given mechanical power Pmech, or we have found out to be 590 watt, and sleep we do not know. Sleep we have to find out. It's a 4-pole machine. Now see, 50 hertz 4-pole, 50 hertz 4-pole gives you 1000 rpm. 1000 rpm induction motors rated speed Means synchronous speed is 1000 rpm and rated speed is 540 rpm. That is too unrealistic. Or am I doing some mistake? I don't think so. 120 f by, no, not 1000, 1500 rpm. Yeah, 1000 is 6 pole, 2 pole is 3000. Yes, 4 plus 15, so 1500 rpm. Induction motor having a full load speed of 540 rpm is too unrealistic, but that's what they have given. So from here what we can find out is the sleep. The sleep is 1500 minus 540 by 1500 which gives 0.6, so 64% sleep. That is too unrealistic. Anyway, so the machine must be cooled with liquid nitrogen if we have to run at this speed. Anyway, so that is what we have. S they have given. Now Pmac, as I said, is 1 minus S times Pg. So from here we can find out Pg is 590 by 1 minus S, which is 1639 watt. So 1639 watt was coming to the rotor, of which we could get only 90 watt at the shaft. So PG we got 1639 watt. Now from here what you can find out is rotor copper loss is SPG, which is 0.64 times PG is 1049 watt. So 1049 watt. Now stator copper loss is 0.3 times this. So stator copper loss is 0.3 times this, which is 315 watt. Now you see here one thing from this diagram, that input power is nothing but Pg plus stator copper loss. So input power is Pg plus stator copper loss. So what we had, this plus 1639 1954 watt. So we have now input power and output power. Input power and output power. So the efficiency would become 90 by 1954. Which is 4.6%. Now, if you look at the options, this is this, not at all in this range. So what I believe is they have made a mistake here. This 4 pole, this should be, can you tell me what this should be? This should be 10 pole. If you go for 10 pole, then the synchronous speed becomes 600 rpm. At these values become realistic. So you have seen the way of doing this. What you do is solve this problem assuming that it's a 10 pole machine and see whether you are getting this result. You should get it. The things will remain the same. Okay. Do this for a 10 pole machine. Everything is same. Just make this 4 plus 10 pole. All right. I will solve this question. Three-phase 440 volt 50 hertz Y connected induction motor, 10 poles, developed 5 HP at 570. Let us see. I think we will need this diagram. Five HP at 570 RPM. See, the question doesn't clearly say whether it develops at the shaft or it develops this much. It doesn't say. But we'll take this as the developed torque, developed power. So Pmax will take as 5 HP. So if this is 5 HP, mechanical loss and iron losses are 0.1 HP and 0.2 HP. Stator circuit loss is this much. Line current is given, calculate the power factor. Okay, so I will use black. So this Pmax, this is given as, I'll not give arrow. All of them are in HP. Oh, this is again kilowatt. Okay. So this is 5 HP and mechanical losses are 0.1 HP. Iron losses are 0.2 HP. So 0.3 goes away, and what we are left with at the shaft is 4.7 HP. Okay. All right. Now, this is Pmax. So 1 minus S times Pg is 5 HP. I will write HP. Sleep we have to find out. It's three-phase 440 volt, 10 poles, so 600 RPM. 600 minus 570 is 30 by 600, which gives you 1 by 20, which is 0.05 sleep. Right? Yes. So 0.05 is a sleep. So 1 minus S is 0.95 times Pg is 5. So what you get, the air gap power, that is the power that is being delivered from the stator to the rotor, is 5 by 0.95. 5.26 HP, which is equal to 3926.3 watt. Now, stator circuit loss is 900 watt. So the input power is the air gap power plus stator copper loss. It is 900 watt. So plus 900, 4826 watt. Now this is what? This is the active power. This is the active power that the motor is drawing. But the motor is also drawing a line current of 7.36 ampere. So root 3 line voltage is 440 volt, as I said, that if nothing is mentioned, it is line voltage. 440 volt line V root 3 VLIL cos phi, line 0.736 times cos phi. This is the active power, 4826. So cos phi that we get 4826 by square root 3 times 440 times 7.36, 0.86. and it is definitely lagging. Induction motor always works in. Okay. All right. Last question for today and this session and this year. And this course. So figure shows the per phase equivalent circuit of a 6-pole 3-phase induction motor. So 6-pole 50 hertz gives us 1000 rpm. Induction motor operating at 50, the air gap voltage Vg across the magnetizing inductance, and the slip is this. How much torque is produced by the motor? Okay. Now this part I will redraw. This is x2. What they have given here is R2 by S. R2 by S I will write as R2 plus R2 times 1 by S minus 1. Okay. So x2 R2 so what happens is some current is flowing. This is the rotor equivalent circuit. This is Vg, which is driving some current. Now some current is flowing. This current is causing some loss in this R2, which gives the rotor. I will move this somewhere else. So the loss happening in this resistance is the rotor copper loss, because R2 is the rotor resistance. And the loss happening in this resistance, whatever power loss, that is basically the developed mechanical power. Okay. So we have to find out the current, how much current is flowing. So 230 volt RMS. So what is Z rotor? Sleep is 0.06. So 0.05 by 0.5 by 6. So 0.22 squared. Mm. So this is rotor equivalent impedance with respect to the stator side, which comes out to be 0.862 ohm. So definitely the rotor current that is flowing, this IR, is 220 by this, right, which is, oh no, 230. So this is Vg by Zeta, 230 by this, 266.86 ampere. Now how much is this? R2 is 0.05. AC is how much? 0.06. somewhere around 0.783 ohm. So the developed power, or the I'll directly do the torque. Okay, so the torque output, there are several things here, pay attention. Now we have to find out the developed mechanical power first. So developed mechanical power, as I said, is I squared R, the power loss in this R2 times 1 by S minus 1 resistance. So it is 266.86 times squared I squared times 0.783. Now this is per phase equivalent circuit. It's a three-phase induction motor. So the total developed mechanical power, mechanical energy is this. I squared R, sorry, not energy, mechanical power is this. We have been asked to find out the torque. So we have to divide this by speed at which the machine is rotating. So we have to find out the speed. So speed will be how much? 1000 minus nr by 1000 is 0.06. So nr is 1000 minus 1000 times 0.06, 940 rpm. So the machine is rotating at 940 rpm. So at 940 rpm, this much mechanical power is developed. So the torque is this by speed, 940 times pi by 30 in SI. 266.86 square times 0.783 times 3 by 940 times pi by 30. It gives around 1699.39. So more or less around 700 Newton, 1700 Newton meter. All right. So that's all for today. So this course is over from my side. My commitments are done. Thank you for joining and thank you for being a regular student throughout the course. I have seen exceptionally low attendance in this course. So this is the third course I am taking in NPTEL. I have never seen um, such a low attendance, such a low response from the student. But anyway, like every time, I'm always lucky to have at least one or two sincere students who at least attend every class. This time also, that's not an exception. So thank you for being that student who is regular in every class. That's all. Thank you and all the best for your future endeavors. Bye bye.
Th- Thank you, sir. Please upload lecture today so I
Sure,
revision.
sure.